In this objective, we're going to talk about 8.5 acid base titrations. So the learning objective states that we should be able to explain results from the titration of a mono or polyprotic acid or base solution in relationship to the properties of the solution and its components. So titration curves. This would be, if we tried to plot the curve of a titration curve, it would involve pH versus volume added. And this can provide a useful summary of the results of a titration. So there's a thing called the equivalence point. So think about equivalence kind of sounds like equal. This is when the moles of acid equal the moles of base. And this is coming from an acid-base reaction. So if I was to write that, a titration would look like this. An acid plus base makes a salt, and this is a dissolved salt. We do need to know that these are the acid and base are solutions, so AQ, and there's still going to be a salt being produced, just it's not going to be a solid like a precipitate reaction. This is not what's happening here. Here will be a dissolved salt, and then we also would make water. So when I talk about the moles of acid equal the moles of base, the moles of acid talking about my reactant acid, and then my moles of base, this right here, they equal each other. So if they equal each other, they will both be limiting reactants. They will all be used up, is what we need to think about it in this case. And that way, if both of them are being used up, all that remains would be a salt, a dissolved salt and water. Now, depending on the type of titration, we can have different types of salts, neutral salts, acidic and basic, and this all comes down to the strength of our acid and base that are reacting. And we'll talk more about that later. So an indicator can help us see when the equivalence point has been reached. And so here, an indicator changes colors based off pH. So indicators we'll talk about more in 8.7, but an indicator is actually going to have in a very, very small amount of some type of weak acid and weak base that changes colors based off pH. Generally, a lot of these indicators are probably some type of transition metal that changes colors, but also indicators can be stuff that's just found around the house. So just thinking about common food items, beets, maybe it isn't as common, tomatoes, cabbage, they all can be squeezed into a juice, and that juice could be an indicator, okay? But that probably isn't going to go with so much of the transition metal, but you can also use household items. Okay, so let's talk about the first one, an acid base. A strong acid, a strong base titration is the first one that we're going to talk about. So here, when we write a strong acid base titration, remember, I'm going to write this more into its general form. So here, if you look here, HA is going to be, I'm going to zoom in. Here, this is going to be our hydrogen. The A will be some anion, so this would be our acid. Then the MOH will be our base. The M will be some metal cation. OH is hydroxide. And then we get the MA, this will be our dissolved salt, AQ. So here, the metal cation and also the A anion will form that salt, okay? And then we also, of course, will be making water because it is a neutralization reaction. So we know that strong acids and strong bases 100% break up. So what it's going to end up being is we know hydrogens release hydroniums, so H3O positive. We know bases release hydroxides, and we will make two waters to balance out the charge. This is what I want us to strive for, is doing this hydronium and hydroxide. But you could also write it as hydrogen plus hydroxide making water. You could also do that as well, but I would lean more towards the first one I write because a hydrogen by itself doesn't actually exist in nature. Okay, that hydrogen is so attractive with water and it's wanting to bond with something, so that's why you actually make hydronium. But you could write it either way. But here, whatever the anion is and the cation, those would break up and cross off with your dissolved salt. Okay. All right. So at equivalence point, we said moles of our strong acid in this case and moles of strong base are going to be equal to each other. And so here in that case, if water is the only thing we get, our pH will be 7. So let's talk about titrations. And we're going to first focus on that strong acid, strong base. So a titration is going to be a technique used to determine an unknown concentration with a known concentration. And here that's able to be achieved because we will reach equivalence point. Okay, so few kind of terminology things. We have something called the titrant and we have something called the analyte. So the titrant will be our known concentration. Please note concentration means molarity, big M. This is going to, the titrant, you're going to be putting in the burette. So this is going to be the burette right here. A burette is going to start with 0 at the top up here and go all the way down accordingly. And so you generally want to fill your burette all the way to 0. So then once you dispense anything, and let's say you dispense 5 milliliters, then you know how much volume you added. Here, our analyte will be our unknown concentration, or you can say molarity. Here, this will be found in the Erlenmeyer flask, which this will be our flask, okay? So, this doesn't only go with a strong acid, strong base, but once we have reached equivalence point, so reach equivalence point, and again, this can be for any titration, we can actually use M1V1 equals M2V2. Yes, this is the dilution equation, but we can use it because it's going to be a 1-to-1 ratio, as in moles of acid equal moles of base. Okay, remember big M will be molarity, V will be volume. Okay, so let's talk about these variables and how we put it in. So here, if we know the concentration of known, this will be our M1. And honestly, it doesn't matter what side you put it on, you just want to be consistent. Now here, this is going to be before the reaction occurs. So this would be before I open up the burette and dispense any of the titrant. Here, before the reaction occurs, you will know the known concentration, the M1, and you'll also know the volume of unknown, your analyte. So volume 2. And that's because look at the flask. You'll know how much volume you have. So I'm going to highlight some things so we can just see it a little bit better. So then this is before the reaction. And then once we reach equivalence point, okay, this will be after the reaction because we'll stop the reaction from continuing. We will get the volume of known added. And this is coming from the burette because remember I told you the burette starts at 0 and then we can see how much we dispensed once we reach that equivalence point using an indicator. This would be our volume 1. So, knowing how math works, after that occurs, if we know 3 of the 4 variables, then we can solve for unknown molarity. This will be M2, okay? And again, M is molarity, which the molarity equation is N over V, and then big V is volume. It doesn't matter if your V1 or V2 is in milliliters or liters, you just have to be consistent. My advice, try to put it in milliliters. All right, let's look at this titration curve. We're going to annotate it just accordingly. So we set at a pH of 7. My hand was pretty steady there. This is going to be equivalence point. Oops. So here, equivalence point, when moles of strong acid equal moles of strong base. So here, this is going to be that net ionic equation we wrote. H3O positive plus OH minus makes water. So all that remains is water. And so that's why the pH will be 7. Now, everything leading up to a pH of 7, this part right here, this is going to be when you have more hydronium than hydroxide. Okay, because again, if you think equivalence points, when they're equal, everything below the 7 will be more acidic. If you could actually change this part right here, H3O positive. So here, the pH is due to excess hydronium. So after it reacts with the hydroxide being added, what remains will be hydronium. So the hydronium will be in excess, hydroxide will be a limiting reactant. Okay, and then everything above will be the strong base, because after the equivalence point, now you're putting more strong base because there's no more strong acid, because at that point we only have water. So here we have more hydroxide than hydronium. So your pH is due to excess hydroxide. And to solve for what the pH is, these are all strong, so you would just take the negative log of either the hydronium to get a pH, or take the negative log of hydroxide to get a pOH, and then do 14 minus that to get pH. Okay, so moving on. Oh, also one thing I wanted to add. Your strong acid in this case is our analyte, and the strong base would be our titrant. And the titrant will always be, I'm going to scroll down. The titrant will always be on the x-axis because you are going to be adding that into your analyte. All right, moving on. So I have an example for you to do, okay? I'm going to read out the problem to get you kind of started. So a titration of 100 milliliters of HNO3 required 45 milliliters of a 0.025 molar solution of KOH. What is the molarity of the original HNO3 solution? So what I would do when you're looking at any of these types of problems, I would write the reaction and determine what's strong, what's weak, what's an acid, what's a base. So we have HNO3, and it's going to react. And the fact that they told you titration, this is an acid-base reaction. So KOH making KNO3 plus water. So here, HNO3 is a strong acid, because remember we have 6 strong acids. KOH will be a strong base. This is a group 1 metal attached with hydroxide. And so they tell us HNO3, we have 100 milliliters. KOH, we have 45 milliliters that we added, and then here is the concentration. So we want to solve for concentration of the HNO3. So if I draw, and again, this won't be pretty, pretend that's my burette. This right here would be the KOH, our titrant. And I know that because I know the concentration. And then in our flask, we will have the HNO3, and we know it's 100 milliliters. So it told us that it required, right here, 45 milliliters. So you added 45 milliliters from the burette to reach that equivalence point, okay? Because if they say titration, you're probably doing something that reaches equivalence point. So here, I want you to pause the video. What is the equation we need to use for equivalence point to solve for an unknown concentration? So putting all of the titrant on one side and analyte on the other. I plugged in all my information, got M2 by itself by dividing 100 milliliters. I got my unknown concentration as 0.01125 molar HNO3. All right, moving on. So we had focused on strong acid, strong base. Let's talk about titration curves that involve something that is weak. Okay, so the first one that we're going to talk about is a weak acid, strong base reaction. So when we approach these types of problems, we know from Unit 4, weak things stay together and strong things break up. Okay, so these are talking about electrolytes, especially towards acids and bases. So when we did a strong acid, strong base net ionic equation, it was hydronium and hydroxide making water. When it comes to this one right here, if you see that it's a strong base, you're going to ignore the cation. Okay, so here, weak acid would be HA. So I'm going to keep whatever the anion is together. This A could be anything but the 6 strong acids. So this could be HF, for example. Now, strong base, we're going to immediately put the hydroxide and ignore the cation, whatever it would have been. OH minus. And here we're going to use a double arrow. I don't know if you noticed, but in the strong acid, strong base, I did one singular arrow indicating none of those reactants remain. And we're only going to have just the water. Here we got to put a double arrow just because you're going to probably have some stuff in equilibrium. Equilibrium meaning they're going to be coexisting, whether it be some of the reactants, some of the products, whatever. Here, knowing how an acid and base work, the acid will donate its hydrogen to the base. So all we're left with is A minus, which will be our conjugate base, plus water. So again, this is weak acid, strong base, conjugate base. Okay. All right, so let's dive in. So I have this titration curve for a weak acid, strong base, and you'll notice there's another point added because it's going to be something that's going to help us out a lot. So let's first start with the equivalence point. You will notice the pH is not at 7. So this is not like a strong acid, strong base. Okay, so let's think about it. If these both will be limiting reactants and none of them remain, what's left is an A minus, which is a conjugate base, and water. So the conjugate base, the second part says base. Here, basic things will have a pH greater than 7. So the only thing that remains at equivalence point is your conjugate base, A minus. So here at equivalence point, when HA and OH minus are used up because moles of HA equal moles of hydroxide. And so here A minus remains. And so here that is going to cause that pH that will be greater than 7. And so what's going to happen is if this is the only thing that remains, you need to rewrite the equation to show that A minus is the only thing that remains in that entire solution after things reacted. So you rewrite the equation, and this is based off objective 8.3. Here, you're just going to show A minus, the weak conjugate base, in weak equilibrium. And honestly, you just flip the reaction. So here, this would be A minus in water. Again, it's weak, making a conjugate acid and base. This is all from 8.3, trying to write reactions that are weak and weak equilibrium. Okay, so let's move on to this part right here. So you see that at equivalence point, I have the volume for equivalence point. You will notice that other line right here is almost about, it's going to be halfway of the actual equivalence point. And we will actually call this the half equivalence point. So the half equivalence point is very, very, very important, okay? So you don't have to put this, but let's say your equivalence point was 100. Your half equivalence point would be 50 because that's half of that, okay? At your equivalence point, this is actually when your weak acid equals your conjugate base. So weak acid equals conjugate base. All right. And I want us to think about this equation right here. This is Henderson-Hasselbalch. Okay. I'll put the brackets real quick. So here, if your A minus and your HA equal each other, the log of 1 will actually be 0. Okay, so here, that tells us pH equals pKa. So at the half equivalence point, your pH is just whatever your pKa is, knowing pKa is the negative log of Ka. So let's talk about the first point now. So here, the first point, this is at the 0 milliliters. This is before the titration occurs. So here, this is before titration. So the only thing before the titration occurs would be our weak acid. So whatever HA is, that's going to help us figure out the pH before the reaction occurs. This is actually from objective 8.3. Here you would just write your weak acid and weak equilibrium, and you can solve using an ice table what the initial pH is if you know the initial HA per se. All right, so anything past 0 is going to be a titration, okay? Because you added something strong to the initial thing, which was a weak acid. So we're going to talk about going from the first dot to the second dot. So let's use this color right here. So everything leading up to the half equivalence point, you're going to have more weak acid than conjugate base. That it may not seem very important right now, but it is very important if you look at objective 8.7. So here, I'm going to write this right here just so we can kind of see this when we're going over all this. So here, if you have more HA than A minus, your HA, if this is a larger value than this, you're going to get a number less than 1. And if you do the log of a number less than 1, you actually get a negative number. So here, your pKa will be added with a negative number, which drops that pH, okay, which makes sense because everything to the left would give us a pH less than the pKa. Now, if we add anything past the half equivalence point, we will have more A minus than the initial weak acid. So here, if your numerator is higher than your denominator, you'll get a number greater than 1. So the log of a number greater than 1 will give us a positive number. So pK will be added with a number, increasing your pH. That's why that increases. And then lastly, we're going to talk about this portion right here. Once you reach equivalence point, any more hydroxide, because remember, you're adding strong base. So if you reach equivalence point, you have none of the reactants remaining, but you want to add more strong base now. Now you're going to have excess hydroxide. And let me put it this way. You don't want the strong thing to win, because what's going to happen is the pH will be based off only strong base remaining. You have to realize strong things 100% dissociate, okay? So what's going to happen is you're going to have some of the hydroxide and some of the conjugate base remain, both bases. And you may think you need to calculate both of these separately or whatever. No, your pH is only due to the strong base because this 100% breaks up. Your A minus, we know, is weak. So it's going to be releasing hydroxides that are negligible. So here, your conjugate base, your A minus, is negligible. And so in that case, you're going to ignore it for pH, and you're only going to look at the hydroxide from the strong base remaining, okay? Last thing that I want to add to this graph, this part right here is going to be your buffer zone. This is when you have, remember, a buffer means that it's resisting pH. And it's resisting pH because your weak acid, and I'm going to look at this equation up here, your weak acid is trying to resist pH changes from your strong base because we know the strong base is going to increase that pH drastically. So your weak acid is able to consume the hydroxide to make some of its buffer components, conjugate base. So here, when you have both of these in equilibrium with one another, your pH in this little area will stay pretty much a plateau, okay? Don't get confused with a strong acid, strong base. I'm going to scroll up for a second. This right here is not a buffer because a buffer has to have weak things remaining. This is not a buffer right here. So here a buffer, again, would have to be a weak acid in its conjugate base or a weak base in its conjugate acid, which in a sense are pretty much the same thing. All right, that is all I want to say for the weak acid, strong base. We're going to talk about the last titration, and I'm going to actually make a second video. So this video is not too long, and it will be over some type of problems you might see with titrations. So let's look at this. We have a weak base, strong acid. So starting off things, let's write the reaction. So here, base plus, and again, the weak base will stay together. Strong acid, I will immediately put hydronium, double arrow, and I'll have conjugate acid plus water. So here I have my weak base, strong acid, conjugate acid, and water. For some reason, I do not have the points here, so if you want to just wing it and add those dots there, that would be great. All right, so we're going to do the same thing like I said, and I'm going to do the same points in order how I did the first one. So here, let's first talk about the equivalence point. So here you can see equivalence point, the pH is less than 7. And so here, when we reach equivalence point, moles of weak base equal moles of strong acid. So since both are limiting reactants, the only thing that remains is our conjugate acid, okay? So here, this makes sense that if we have a conjugate acid, that's the only thing that remains, it's acidic, so its pH will be less than 7. So here, you're going to rewrite equation, and this is coming from objective 8.3 to show my conjugate acid, which is now the weak acid, in weak equilibrium. And so, yeah, it will be dissociating in a small amount. Sorry. So we have to make sure to show that. All right. Next point, let's start with the first. So here, if you guys write volume equivalence point. Now let's talk about the half equivalence point. So again, if your equivalence point was 50 milliliters, your half equivalence point would be half of that, which would be 25. So here, at this point right here, your base, your weak base, will equal your conjugate acid. Okay, now this is going to be kind of hard to understand, But here, if they equal each other, remember that Anderson-Hasselbalch on your equation sheet starts with a pH. You could also write a POH version of it. This one is not on your equation sheet, so that's why I would probably just recommend going based off whatever the pH version would look like, just something to consider, okay? So in this case, with the weak base and conjugate acid, here POH equals pKb. So here you have to realize our y-axis is based off of pH. So to get pH, we will do 14 minus POH, okay? All right, so now let's go back and talk about the first point. Here, this is before the titration occurs, so only weak base begins. This is not a titration yet. So here, to write this in weak equilibrium, base in water, we'll make HB positive plus OH minus. And so here, this would be based off objective 8.3, and we could solve that if we knew the concentration, okay? All right, so let's talk about first point to second point. Here, you're going to have more weak base than conjugate acid. And then, after equivalence point, we will have more conjugate acid than weak base. Again, kind of following the trend from the previous one. And here, I'm kind of skipping around. This right here will be our buffer zone. Because again, in the buffer zone, it is resisting pH changes from that strong thing being added. And so here we'll have that plateau. Because honestly, when we make a buffer, it's anywhere with the green and the red. Okay, this part right here. Here we're going to have both of the buffer components in equilibrium, and this correlates to a buffer because a buffer needs its weak acid with conjugate or weak base and conjugate. In this sense, weak base and conjugate. All right, and then lastly, anything past equivalence point. Here, this is going to be excess strong acid remaining. So here, the conjugate acid, although remains, will just be negligible. So here our pH will just be based off the strong acid remaining. Just honestly ignore the conjugate acid because it will only be dissociated in a very small amount and won't have anything to do with the actual pH, okay? Overall, I know this is a lot. I would practice writing and drawing all these titration curves so you can get a better understanding on how these curves help us understand the conceptual and the mathematical components that you will need for Unit 8.